In this video, we're going to look at a different twist on double displacement reactions in which one of the products of a double displacement reaction undergoes a subsequent reaction, resulting in 3 different products rather than the usual 2. If we treat HCl in this first reaction as our AB and NaHCO3 as our CD, we can make a fairly standard prediction about what our products are going to be. Now, in some of these reactions, the polyatomic ion is probably not going to appear in a standard polyatomic ions table, but we also don't need it to because we can figure out what the charge is. We know that the charge of sodium is +1, which means to balance out this charge, HCO3, or hydrogen carbonate, is going to have a -1 charge, and therefore we now know how much positive charge from the other cation we need in order to balance this charge. So, if we treat this as a standard double displacement reaction, we can switch the cations H plus and Na plus in order to give us our 2 products. The first one is going to be Na paired with Cl, making standard NaCl, and because we're taking a hydrogen here from HCl and adding it onto a polyatomic ion that already has a hydrogen, we can write this as H2CO3, which you'll recognize as the compound carbonic acid. Now, if we want to check the solubility of these compounds, we can quickly do that. So if we check chloride, we can see that sodium does not fall on the low solubility ion side, which means that it must be here, which means that NaCl is going to be a soluble compound, but we knew that already. If we check our second compound, carbonic acid, we know that the polyatomic ion carbonate is here, and we see that hydrogen as an ion, H+, falls on the soluble ions category, which means that H2CO3 carbonic acid is going to dissolve, and because carbonic acid is an acid, this is no surprise as most acids tend to dissolve very well in water. So normally this would mean that because we don't have a precipitate in this reaction, we are not going to see any observable change. But as we will see in this subsequent reaction, that's not exactly true. Whenever carbonic acid is produced by a reaction, there is a chance that the carbonic acid will undergo a subsequent reaction in which it decomposes to form liquid water and carbon dioxide. Now, we know that carbon dioxide is a gas at room temperature, and we are actually going to be able to see this in the form of bubbles. If you've ever seen this reaction before, this reaction involves sodium hydrogen carbonate, which is better known as baking soda. So instead of using concentrated hydrochloric acid, if you were to drop vinegar on this, you will see a lot of bubbles forming, which is actually the decomposition of carbonic acid into water and carbon dioxide. Now, because these 2 reactions occur one after the other, what this means is that carbonic acid that is a product in the first reaction, we can see it appearing as a reactant in the second reaction. And so whenever you have, in math, for example, whenever you have a number that appears in the numerator and then appears in the denominator, you can cancel it. And in chemistry, we can do the same thing. So because carbonic acid appears in the products in the first step and then becomes a reactant, we can cancel it from both steps. And if we were to write the overall reaction, it would not appear because the carbonic acid has broken down into liquid water and carbon dioxide gas, with the dissolved NaCl being the rest of the equation. And we see here a double displacement reaction that, because of this subsequent decomposition reaction, produces 3 products rather than the usual 2. There are 2 other situations in which this occurs. For example, if we treat HBr as our AB and KHSO3 as our CD, again, we can figure out what the charge of HSO3 is because we know the charge of potassium as an ion is positive 1, and therefore the charge of HSO3 will be negative 1. So if we do our AB plus CD goes to AD, which would be H2SO3, and KBr would be our CB. Now, I'm not going to bother with the solubility table check, but again, we can see usually whenever you have hydrogen as the positive ion paired with a polyatomic ion, you get an acid, and if you check the table, you'll see that sulfurous acid, this acid here, is soluble, likewise with KBr. However, what we're interested in is what happens to H2SO3 after this reaction is completed. If you follow the same pattern as carbonic acid's decomposition, we can pull water out of this compound here, leaving us with another gas, sulfur dioxide, which is actually a common industrial pollutant that leads to the production of acid rain. So again, we see a double displacement reaction that produces a very specific acid, which can then undergo decomposition in order to form water and a gas. And because sulfurous acid appears as a product and then as a reactant, we can cancel it, and therefore it does not appear in the overall reaction here because it has broken down into liquid water and sulfur dioxide gas. The third example that we see below is a little bit different because we don't have a polyatomic ion that looks like sulfite or carbonate. So if we treat ammonium chloride as our AB and sodium hydroxide as our CD, that would mean that our AD compound is ammonium hydroxide, NH4OH, and our CB is going to be NaCl. We know that NaCl dissolves completely in water, and if you check the solubility table, you'll find that ammonium hydroxide also does. However, in this case, the ammonium hydroxide can actually undergo a decomposition reaction. So again, we see a common pattern here of pulling water out of an ionic solid. So if we pull water out of this compound here, you'll find what we have left over is NH3, also called ammonia, which is a highly poisonous gas, but also surprisingly easy to make from this reaction here. So as with the previous two, we have an ionic compound that undergoes a subsequent decomposition. And because ammonium hydroxide appears as a product in the first step and a reactant in the next step, we can cancel it from the overall equation and write the products that remain, which would be dissolved NaCl, ammonia gas that is produced when ammonium hydroxide decomposes, and liquid water that remains. So the conclusion that we can reach here is that double replacement reactions that produce sulfurous acid, carbonic acid, or ammonium hydroxide can undergo subsequent decomposition reactions in order to give us at least one gas and water as a waste product. That concludes our videos involving the twist in double displacement reactions. So using this knowledge, you can try the practice problems below that require you to identify whether the reaction occurs, and if it does occur, what the precipitate is, and whether any subsequent reactions occur in the form of a decomposition reaction, as we looked at in this video.